let's go ahead and start back from lunch. We have Vladimir Smirnyagin from Yale, and he'll be headed over to Virginia for the fall.
Yeah, hi everyone. First of all, thanks to organizers for the invitation. I'm Vladimir, and today I want to present this piece, which is titled "The Growing Importance of Universities for Patenting and Innovation." This is joint work with Todd Sherman from the Minneapolis Fed, and so I want to switch gears somewhat, like back to the empirics. We've seen some theoretical work presented by Carlos. I'm going to show you a bunch of regressions. In my other work, I don't really do a lot of empirical stuff, so let's see how smooth it's going to be when I'm like describing regressions. But all the feedback is welcome and will be appreciated. So the point of departure for this project was the kind of basic observation that universities play an important role in conducting research, right? So if you look at basic research, for example, in the United States, universities would account for approximately half of that. And there is some well-established work which documents that universities have a spillover effect for the innovative activity of nearby inventors. So what is this paper about? I guess we make two contributions. So the first one is to construct an MSA year panel dataset which spans 4 decades of data for the United States. So from 1972 to 2015. So maybe so this paper has been hibernating for several years, so probably we could update and extend it over for a couple of additional years. But basically, the data set covers nearly the universe of MSAs, the metropolitan statistical areas in the United States, 355 of them, and it covers major research schools in the states. We also complement this information with different measures of income at the city level, population, the school quality, and others. So, and the second contribution of this project is to document the growing spillover effects of the university R&D on the patenting activity of nearby inventors since roughly the 1980s, using this constructed data set. So that's basically what we do, what this paper is about. Yeah.
What is basic research?
Yeah, so this is an excellent question. So think about the following. If the researcher studies, say, what are the qualities of the human body which affect the blood coagulation, that will be classified as basic research. If this researcher is, say, studying how does COVID-19 affects blood coagulation, COVID-19 vaccine affects blood coagulation, that will be counted as applied research. So more like if the research has like some particular application, that will be counted as an applied research. If it's like more abstract, that will be basic. All right. So preview of the results. Given that some MSAs, some cities don't really have a research-intensive school, we would like to think about the effect of the R&D expenditures on the patenting activity, or decompose it in 2 margins, the extensive margin and the intensive margin. So what is the extensive margin? The extensive margin is basically the patenting advantage of having a research-intensive school in the city. So we show that basically along the extensive margin, the advantage of having a research-intensive school has nearly doubled over 4 decades. And intensive margin, that's an elasticity of patents with respect to university R&D. And we show that along the intensive margin, the spillovers have nearly tripled over the sample time period. So we want to claim that this captures, in some sense, the spillovers of R&D on the patenting activity, and we sort of back up this reasoning using several ways. So first we show that this time trends, right, the doubling of the extensive margin and tripling of the intensive margin those are robust to a variety of other MSA and university characteristics. We also show that the results, they hold by the field of study, so we can split R&D expenditures by the field of study, as well as we can also classify patents by the field of study and show that these results basically hold field by field. And we also show that the results are stronger in cities which conduct more basic research. So using this combined evidence, we kind of that reassures us that these time trends, those correlations, they capture some spillovers going on between the R&D and patenting activity.
So
Yep.
are you excluding the patents that the university owns? Is it
Yeah.
only patents that are not?
Yeah, so I'll show you later that university patents, they account for a small fraction of all patents granted. So even if you exclude them, the results are they are roughly the same. And the final piece of today's talk, I want to talk about the Bayh-Dole Act, which is one of the major reforms which stimulated the patent activity in the United States. It took place in the 1980s, and essentially that reform allowed researchers to get the rights for the invention, even if this invention was funded in part or in whole by the federal government. So before the act, if you invent something, then the government would just claim the rights for this patent. And after the implementation of this act, the federally funded research became the property of their inventors. And we showed that this act, like the implementation of this act, accounts for about 20% of the extensive margin effect which we find in the data. Okay, so those are the results. Let me speak a little bit about the data. We want to construct a panel which is sufficiently long, and there is no unique data set which would be, directly giving you that information. So we had to rely on several data sources. So the main data source is the National Science Foundation. This is the survey of universities in U.S. institutions since 1972. And there is basically the selection of those schools, not every institution in the United States is covered by the survey. So there's some threshold of the amount of R&D expenditures the school has to make to be included in the survey. So the threshold varies over time, but roughly over the last several years, the school has to make like $150,000 in R&D to be included in the survey, which is a pretty low bar. We focus on research-intensive schools. That means, in our definition, is that the cumulative R&D expenditures are more than $10 million, which is a pretty low bar too. And the NSF data provides us with the splits of R&D expenditures by source, like do the money come from the federal government, from the state, or from other sources. We have splits of the R&D expenditures by field of study, like agricultural, medical, mechanical, and others. And for the last 5 years or so, the data also provides splits of expenditures by basic research and applied research, something I mentioned earlier. So we complement NSF data with two wide-ranging surveys, the Haggis and IPADS. So let me see if I remember the abbreviations correctly. So Higher Education General Information Survey, that's Haggis, and its successor IPADS, which is Integrated Post-Secondary Education Data System, something like that. So those surveys provide information on the location of the school, as well as other university level characteristics like fall enrollment, so we can control for the size of the school. So the second key variable in our analysis are clearly patents. So, and there is no unique data which would provide you the number of patents granted in a given city over the last 40 years. So we kind of combine three data sources. So the last 25 years, from 1990 to 2015, are the easiest because U.S. Patent and Trademark Office provides just tabulations, how many patents have been granted in a given year in a given city. So that's easy. The second, for the years from 1976 to 1989, we use microdata from the National Bureau of Economic Research. And we basically map inventors to their cities, and then those cities to counties, and those counties to MSAs. And for the first 4 years, we use historical patents records compiled by, there's a paper by Petroleum co-authors. So that allows us to construct basically how many patents have been granted to inventors located in a given city over the 4 decades. All right, so here in this slide, I'm showing you the summary statistics of the resulting panel. So I report the stats for 4 selected years. As you can see, the number of MSAs is 355, which kind of stable over time. The number of universities is ranging from 395 to 500, so it slightly increases over time. And this reflects the fact that the threshold for inclusion of the university in NSF survey have been sort of declining over time. So we see more, or alternatively, schools started spending more on research, and that allowed them to show up in the survey over time. So that's why we see like a slightly growing number of schools. The distribution of universities across patents is highly right skewed. So we see that the median is approximately 20. The distribution of cities across with respect to patents is highly right skewed. We see that there are like the typical city would have only 20 patents, whereas like the 99th percentile, think about Boston and New York or Los Angeles, they have like 2 orders of the magnitude more patents. And in terms of the R&D expenditures, we also see highly right skewed distribution. Typical school has a very low R&D expenditures, whereas like schools in the right tail, they invest much more. Think about, again, MIT, Harvard, and others. All right. So, yeah.
So when you register a patent, is there any regulation that could potentially provide you incentives to do it somewhere else that is not where you live? Like, I don't know, is there maybe you want to register it in Delaware because there's no taxes.
So I guess we're like looking at maybe. The short answer, I don't know. If someone knows the answer, I'll be curious to know. But
I mean, because you're assuming that the inventors register the patents where they live. That's how you're gonna impute that.
That's what we do. That's what we do for this year's, from 1976 to 1989. We use the microdata, and then the microdata is at the patent level. So we see like who is the inventor, the first name inventor, and we know his location or home address, and we use that information to map him into a specific city. I guess I'm not sure if there are some incentives to move somewhere else to patent, but I guess it might be an important point to consider. All right, so this slide basically shows our results in 2 figures. So on the left-hand side, you see the extensive margin, which is basically captures the effect of having a university. So this is the log difference between the number of patents in cities which do have a research-intensive school, less the log of patents in those MSAs which do not have a research-intensive school. As you can see, it was approximately 50% more on average, a 50% advantage of having a research-intensive school back in the day, in the early 70s, but then this advantage nearly doubled over 4 decades. So this is not controlling for anything, it's just I'm looking at just raw data. And on the right-hand side, you see the picture of intensive margin. This is basically the elasticity of patents with respect to R&D expenditures. And the elasticity was about 10%, and then it nearly tripled over the course of the time. So we want to claim that some of that rise is capturing this rising spillovers from university to local nearby inventors. Another way to look at the data is to sort MSAs, sort cities with respect to the cumulative R&D expenditures of the universities located in those cities. And here you see a bunch of lines. The black line, this is the number of patents per 1,000 of people for cities which do not have a research-intensive school. Then you have another line for those cities which have where schools cumulatively spend less than $10 million, between 10 and 100, 101 billion and more than 1 billion. So two things to notice here. So first of all, if we look at the lines corresponding to MSAs with no research-intensive university and those which have like moderate amount of R&D expenditures, then there is a patenting the advantage of those R&D expenditures is very muted, and if anything, it shrinks over time. So if you compare, say, the purple line and the black line, they become closer over time. However, if you look at MSAs which have a lot of R&D expenditures, then we see the widening gap. So I guess our story is about the patenting advantage of MSAs such as Baltimore and New York or Boston, which have like very highly intensive, universities, and in those cities the number of patents have been increasing much faster over the last 40 years. All right, so now I'm going to get to some regressions. Basically, I've shown you some raw data, but the raw data has a lot of confounding factors, and this is our attempt to sort of control for those confounders. So to study the extensive margin, we want to regress the log of the patents granted. So PAT IT, this is the number of patents granted in CTI in year T, and we project that on the dummy variable, which is 1 if that city has a research-intensive school in a given year T. And the coefficient of interest is beta 1, which measures how fast this extensive margin was changing over time. All right? And so here in the table you see 4 columns. The first 2 columns correspond to the situation when we measure this dummy with respect to any research-intensive school that the city can have. And we see here, for example, that extensive margin was about like 5% in 1972, and it increased at this rate over the last 4 decades. So, in other words, the extensive margin grew from about 5% to 52% if you don't control for other confounding factors. However, if you include confounding factors like population, income level, and such, you would see that the coefficient of beta 1 shrinks dramatically, and it's barely significant. So we hypothesized that it might be the case. It's not like any research-intensive school which matters, but coming back to this figure I've shown you earlier, is like really the story about very highly intensive cities, right? Like Boston, MIT, Boston, New York, and Los Angeles. So we are redefining the dummy variable D's in a way that reflects whether the city has a top 250 research-intensive school, like really a research-oriented university. And in this case, no matter whether we add the controls or not, the beta 1 remains to be sizable and economically significant. So the advantage of having a top 250 university grew from 24% to roughly 107%. So the extensive margin increased dramatically over time. So now the intensive margin. The intensive margin study looks into the elasticity of patents with respect to R&D, and we are projecting the patents on the R&D expenditures, like cumulatively done by universities located in a given CTI in year T. And again, we're interested in this beta 1, which captures the time trend. In the first column, we just don't have any controls, and we find that the time trend was sizable and economically significant. Then, in the second column, we add some additional controls, both at the city and the university level. For example, we include the population at the city level, the total full enrollment to control for the size of the school. We also add the income level at the MSA level, at the MSA level, as well as the school quality, which is measured by SAT scores. And we also interact them with time. And we find that basically the beta 1 remains to be highly significant and only marginally loses in size. So it means that the incentive margin also increased dramatically, controlling for those additional variables. A related concern, it might be the reverse causality. Is it the higher R&D expenditures like induce higher innovative activity, or is it the other way around? You have like very highly research-intensive schools, and they attracted more inventors over time. So what we do is we want to fix the right-hand side variables at the level of 1980, and we repeat the same exercise. Basically, this implies that this our story is likely to be the truth. Is like the higher R&D expenditures led to more patenting rather than the other way around. Okay. Okay, as I mentioned, our data allows us to look into fields. So NSF provides a split of R&D expenditures by different fields. Like we consider 5 of them: agricultural, chemical, electrical, mechanical, and medical. And also in the patent data, we can classify patents into those 5 fields too. And we find that the patenting is tightly linked to R&D in the same field. For example, here you see that semi-elasticity is always positive and highly significant, and it ranges from 0 to 4, say for the medical field, and to 1.65 for the electrical field. We also find that the R&D done in other fields has little or even negative effect for the patenting activity in a given field. For example, here, let me click the small button. Here I show the results for the number of agricultural patents projected on the total R&D expenditures, as well as the share of R&D made in different fields. You can see here is that the share of R&D in the agricultural field is a strong predictor for the number of patents in agricultural field. Other fields have sometimes even negative effect or statistically insignificant effect. So again, this reassures us that the rising intensive and extensive and intensive margin, they capture the rising spillovers from R&D to innovative activity. Okay. Yeah, we also should look at the growing link between patenting and R&D expenditures at the field level. Here, there's a lot of numbers, but I wanted to just say that the interaction between the share of R&D in a given field with time, like these coefficients over here, they are sometimes even negative, but if there's this coefficient is positive and highly significant for the medical field, which reflects the fact that medical field accounts for a big fraction of total R&D expenditures made in the United States. Okay, so then coming back to the Carlos question about university patents, it might be the case that it's just university professors which patent those things, and this fully accounts for the patterns we are seeing here in the data. It turns out that the share of patents which are accounted by people who are affiliated with universities indeed grew substantially over 4 decades, but it did so from a very small base. Like, for example, back in 1972, the number of patents accounted for by universities is less than 1%, and it grew substantially by a factor of 5, but it still remains to be a small fraction of all patents. So if you just basically keep, subtract them and rerun all the regressions, you're going to find roughly the same estimates. All right, so National Science Foundation data sets provide a split between basic and applied R&D expenditures for a limited number of years, so after 2010. As I said, basic research, this is something more abstract, and applied, this is something you can directly use for commercial purposes, so to say. And there is a tremendous heterogeneity in the amount of basic research conducted across schools. So 60% of total research is allocated to basic research on average, and the interquartile range is big. Like the schools in the 25th percentile spend 41% on basic research, and schools in the 75th percentile spend twice as much. And next, we're interested in whether the basic research, or the share of basic research, is a strong predictor of patents in a given MSA. So we are regressing the log of patents on the total R&D expenditures, as well as the share of R&D expenditures which are accounted for by basic research. And we find that the coefficient in front of the basic R&D share is positive and highly significant, no matter whether we control for other confounding factors or not. And the economic interpretation of those numbers is that a city at the 75th percentile of the distribution across the basic share makes 15% more patents than the city in the first quartile. And another thing I want to point out here is that the coefficient on the total R&D expenditures and the share, they're similar in magnitude. So if the university increases R&D through applied research, that will have an offsetting effect on patenting, because the share of the basic research will fall. So that's what we found here too. All right. So now the final part of the stuff which I have is about the Bayh-Dole Act. This is the major reform which took place in 1980, and some amendments were introduced in 1984. Just like I mentioned earlier, before the implementation of this act, if the innovation was financed in whole or in part by the federal government, then the federal government will claim the patent rights for that invention. And after the implementation of this act, essentially the inventor could retain the patent rights on the invention, regardless of the source of funding. So what we are interested here is that we want to understand what is the impact of this policy was on the innovative activity. And our data is granular enough to answer this question. Okay, so here I plot the distribution of cities with respect to the share of the federal R&D over time. And we see here a tremendous heterogeneity. Like the typical city would have approximately 60% of research being financed by the federal government. And the city in the top quartile would have nearly twice as much share of the federal R&D as compared to the cities in the bottom quartile. And this difference between the cities, this heterogeneity, has been persistent across years too. All right, so to assess the impact of the act, we run the following regression. So we regress the number of patents on the total level of R&D expenditures, as well as the interaction of there with time. We also control for the share of the R&D expenditures financed by the federal government as superscript F. And the coefficient gamma 0 captures the effect of the how important federal share is. And then we also want to see whether the effect of the role of the federal R&D has changed after the act has been implemented. So we interact the share with the dummy, which is equal to 1 if the time period is after 1985, when the full act has been implemented. We find here is, oh yeah, so I'm sorry, I don't know what happened here, but it's supposed to be 6 to 10%. We find that the gamma 1, the coefficient of interest, is positive and statistically significant, no matter whether we control for confounding factors or not. And we also include MSA fixed effects, so we're looking at within city variation over time. But we find that the Bayh-Dole Act indeed had a statistically sizable effect on patenting activity, as the coefficient is significant at 1% level. And putting those numbers into perspective, we find that the Bayh-Dole Act had it can account for about 20% of the extensive margin effect, which we documented earlier. So I guess I'll just wrap up. What we did here is that we documented a growing link between university R&D and local patents since 1980s. For that, we used a new MSA year panel spanning for decades. I argued that along the extensive margin, the effect doubled. Along the intensive margin, the effect tripled. We also find that the effect is stronger in MSAs with university conducting more basic research, and we kind of provide additional evidence in favor of spillover effects by studying the relationship between patents and R&D within fields. And the timing of the time trend change suggests an important role of the Bayh-Dole Act, which led to about 6 to 10% more patenting in a typical MSA. So that's what I have for today. I'm a little bit early, but I'm happy to take any questions. Yeah.
What was the effect of the Bayh-Dole Act on the composition of funding, or like the funding environment overall? Have you tried using it, the share or the levels or the
So you're asking, okay, so after the 1980s, has the share of the federal R&D changed substantially, or?
Yeah, it seems like it changes the incentives to deliver federal aid and to take up federal aid.
That's a good question. We haven't looked into that, but I guess we could to study more. Yeah, definitely the incentives have changed. We just did not quantify that.
I didn't quite follow. What are you doing about population? These MSAs are very different population.
Yeah, in all the regressions, when we see the control with the check mark, we include the population as well as the interaction of population with time. So we control for the size effects.
Is that in a log?
Yeah, the log. Yeah, it's a log. So all the variables are logs, other than shares. All right. Thank you. Thanks for all the questions.